So the task of language modeling is associating probabilities to sentences that could appear in natural language. If you see a sentence, what is the probability that that's actually a sentence from natural language and it's not some random sequence of words or some random sequence in general? So you are associating probabilities to sequences or to sentences and making the ones that are natural looking more likely. And that's the language modeling task. And why would you do that? Because when it comes to language, you have a lot of data on the internet, and these data are unlabeled. And a good task is actually associating probability to sentences and make them more likely. And once you're able to write a model for your language, then you're going to be able to do transfer learning. You're going to be doing classification. You're going to be doing question answering, summarization. All of these tasks, the downstream tasks, they are labeled, but labeling is costly. Therefore, you usually deal with small data. So you have small labeled data, large or big unlabeled data, and you want to do transfer learning. So we are not interested in language modeling for the sake of language modeling. We are interested in it because it's going to help us do transfer learning. And this is one of the first papers that actually tried to do that. To be honest, when we were talking about word representations, we were learning some word representations from unlabeled corpus, and then we were transferring those word representations to downstream tasks. The idea here is, can we do the same thing for sentences? This is an assignment for you to watch that YouTube video. So I'm going to go through this really fast, and then you can ask questions. What is the big picture here? With word representations, you're associating a vector to a word. It means that every single word is going to have one and only one corresponding vector, and vectors are actually meanings. It means that for each word, you're associating a single meaning. But we know that in natural language, a single word can end up having different meanings depending on the context. A good example is bank. Bank in one sentence can convey the meaning of a place that where you hold or put your money. Depending on another context in another sentence, it could mean a river bank. Same thing for play here. Play could mean playing sport, or it could mean playing an instrument, a musical instrument. Depending on the context, the word play could have different meanings. Can we actually have a model that takes into account the context of a word, and then it's going to associate to it different meanings? And that's where the Elmo model is going to help us. What are you going to do? You're going to start with an unlabeled corpus, which could be Wikipedia, which could be texts from the internet using Common Crowd. So you have plenty of data to work with. They are unlabeled. And your data are in the form of sequences, and you want to make your data more likely. So you want to increase this probability. One cool thing about language is its sequential nature. At the same time, we have this chain rule for probabilities. We know that chain rule from calculus is really helpful for training deep neural networks, and that's going to give us backpropagation. So that's one of the engines behind the success of deep learning, backpropagation chain rule from calculus. Here's another one, the chain rule for probabilities. We can decompose that probability into, if I give you the first word, you give me the second word. If I give you the first two words, you give me the third word, etc. And this is exact. And we know that we can model that using LSTMs or stacks of LSTMs. Equivalently, you can go backward, or you can actually go in any order that you like. Write down your chain rule in any order that you like, in any perturbations of numbers from 1 up until n. If you go backward, you're going to take the last word, predict the one to the last, and then keep going backward. And that's going to give you backward LSTM. And your objective function is predict the next word, predict the previous word, a summation of the two. And then you can optimize that over your tokens, over the LSTM, and over the softmax. And where do we need the softmax? We need it for this classification. So there is a natural classification built into natural language processing or natural language modeling, which is predict the next word out of your vocabulary. Take a look at your entire vocabulary, which could be the next word. And then you can do your training. Once the training is done, for each word, for instance, here you have Chico, Ruiz made a spectacular play on Aluski's grounder. This could be your sentence per each word. If you push that through your LSTM, on top of each word, there is going to be a vector representation. And that vector representation is going to know about its neighborhood. It's going to know the context. And that's the way that for play, you might end up having different vectors depending on the context. And those vectors, you're coming out of your LSTM and you're calling them Elmo. How do you use it in practice? Maybe you want to do question answering. Maybe you want to do sentiment analysis. Not only you're going to give as input your word vector representations, you're going to put as input these contextualized word representations as well. And then on top of that, you can put a classification head for your downstream task and do some optimization, fine tuning. Was everything clear? So I'm going to leave this as an exercise, as an assignment for you to watch that video for more details, and then go through these data sets and do EDA on them, exploratory data analysis. Any questions about Elmo? Was everything clear? Okay, perfect.